Lesson 11.3, Inference about two population means that are independent samples. The objectives for this lesson is to test hypotheses regarding two population mean from independent samples and construct and interpret confidence intervals about the difference of two independent means. Let's look at our overview sheet. So today we're working with quantitative for two populations that are independent. We will be covering this section right here in this lesson, just so you have an idea of where we're at. There are 4 criteria for testing hypotheses regarding the difference between two population means that are independent samples. 1. The sample is obtained by simple random sampling, or the data result from a matched pairs design experiment. If it is a matched pairs design, that means it's dependent. So if we find out that it's matched pairs, you're going to have to use the dependent hypothesis testing. Here, the second criteria is that the samples have to be independent. So for this one, it has to be simple random and independent. The third criteria, the sample data come from a population that is normally distributed with no outliers, or the sample sizes are large. So either N has to be normally distributed with no outliers, or it has to be greater than or equal to 30 for each sample because of the central limit theorem. The fourth criteria, for each sample, the sample size is no more than 5% of the population size. So sample N is less than 5% of population N. Welch's t-test. There are 5 steps for testing a hypothesis regarding the difference between two population means for an independent sample. For step 1, determine the null and alternative hypotheses. The hypotheses can be structured in one of the 3 ways. Here we have a two-tailed, a left-tailed, and a right-tailed. The only thing that's really going to be changing in any of these hypotheses is this symbol for your alternative hypothesis. Note that mu sub 1 is the population mean for population 1, mu sub 2 is the population mean for population 2. Step 2, select a level of confidence alpha depending on the seriousness of making a type 1 error. Step 3, use number 18. You can check for normality and no outliers if n is less than 30 on the calculator sheet to obtain the p-value and test statistic. Step 4, if the p-value is less than alpha, reject the null hypothesis. If the p-value is greater than alpha, do not reject the null hypothesis. And then step 5 is to state your conclusion. So let's look at an example. In the Space Lab Life Sciences 2 payload, 14 male rats were sent to space. Upon their return, the red blood cell mass in milliliters of the rats was determined. A control group of 14 male rats was held under the same conditions except for space flight, as the space rats and their red blood cell mass was also determined when the space rats returned. The project, led by Dr. Paul X. Callahan, resulted in the data listed below. Does the evidence suggest that the flight animals have a different red blood cell mass from that of the control animals at the alpha equaling 0.05 level of significance? Alright, so we know we need to do an hypothesis test, but which one exactly? Because eventually these are going to be all thrown together on your final, so you're going to need to determine which one you use. First step, I would ask yourself, is it quantitative or qualitative data? This is quantitative, right? We're given numbers, so we're looking at the quantitative. Do we have one population or two populations? Here's one, here's two, so we have 2 populations. And is this data dependent or independent of each other? They are independent. The red blood cell of the space compared to control does not depend on one or the other. So once you figure out those things, you can go to your overview sheet, go to quantitative. Here's one population we said it's two populations that were independent. So you're going to use number 18 because we're looking at hypothesis testing. Okay. Also, we're looking at the flight animals that have a different red blood cell than the control. So flight animals is going to be mu sub 1 because that comes first in the sentence, is different, and then the control is mu sub 2. We're going to use that later on step 1. But first, let's verify the conditions. Is it simple random or matched pairs? Well, we know it's not matched pairs because it's not dependent. This would be simple random. And it doesn't state in here, so we can assume. That's a fun thing about stats. We can assume it's randomly sampled. Criteria 2. Samples are independent. Step 3. We have 14 in each sample, so we do not know if it is randomly or normally distributed or not. So we're going to have to use number 18 on our calculator sheet to check. Let's pull up our calculator sheet and go to number 18. Here we're going to go to Stat, Edit, and type data into List 1 and List 2. So mu1 is going to go in List 1 and mu2 will go in List 2. So it is vital to identify which one's your mu1 and mu2 because it could get switched around. So again, mu1, this is going to go in your List 1, control will go in List 2. Because they are independent, the order does not matter. It's another reason why we don't write mu sub d here, because we're not matching up anything. So if you notice, mu sub d is only for your dependent. Okay, so type that into your calculator. Again, we're checking for normality and outliers. So go to second, y equals, make sure it's on, select the last graph, data list L1, hit graph, then zoom number 9. So this looks pretty straight, so we can say that that is normally distributed. And then part G says do A through F for list 2. So do this all again for list 2. I think my calculator got stuck. Okay, now we're going to change it to list 2. Graph. Again, this looks like a straight line, so we can say that's normally distributed. All right, now let's look for outliers. Change it to the 4th graph. L1, graph, zoom, number 9. I'm not seeing any outliers here. There's no dots beyond these lines. And then again, check your outliers for list 2. And readjust your window. And again, there are no outliers. So we can say each sample is normally distributed and no outliers. And number 4. Is 14 less than 5% of all the rats out there? Yes. So each sample is no more than 5% of the population size. So each sample again is 14. is no more than the population size, which we're talking about is rats. All right, let's get into the steps. Okay, like I said before, nothing's going to change. They're all going to stay consistent besides the symbol for the alternative. So I'm going to write everything down that we can. Now, what symbol is going to go here? Keyword is, and I circled it, different. So we're going to cross that out. Step 2, state our alpha. That was stated in the question. It is 0.05. Step 3, figure out the t-test and the p-value. So now we're on 18 again at the very bottom. So we can go to stat, tests, and before we put data in, so that should be highlighted. mu1 was in list 1, mu2 was in list 2. Keep the frequencies at 1. We're looking at not equal, and keep the pooled at no, and go down, hit calculate. T is negative 1.44, p-value is 0.163. Remember, p-value, this is probability, so you can never be negative and it can never be greater than 1. Step 4, take your p-value, compare it to your alpha. It is greater than alpha. When it is greater, you do not reject the null hypothesis. Step 5 is to state the conclusion. We can say there is not sufficient evidence to conclude that the flight animals have a different red blood cell mass from the control animals at the alpha equaling 0.05 level of significance. Right? So we're not rejecting the null. So I always like to circle the one that we're talking about. And then for a little bit more of an explanation, the p-value of 0.1627 means that if the null hypothesis, the mean difference of red blood cell mass in the flight group and the control group is 0, is true, we expect similar results similar to the ones obtained in about 16 out of 100 repetitions of this experiment. The results we obtained are not unusual if the null hypothesis is true.